All right, sir. So the first thing that we begin with is the idea of physics. What do we study in physics? Yes, sir. So we said that we study quantities. That is all that we do in physics. In order to understand a quantity, the minimum most that I will require is that I will need a magnitude. I will need magnitude for the quantity in order to express like how much is it, and then in order to differentiate one quantity from the other, or in order to fully express that what is it exactly that I am calculating, I'll have to mention unit with it. Okay, this is the utmost basic that I would require in order to express a quantity. I might need something else as well, which is direction. So if I need just the first two to express the quantity, then such a quantity is called scalar quantity. And if I need uh, magnitude, unit, as well as direction to express the quantity, then such a quantity is called vector quantity. Right, sir? Are you following? All right. Then, sir, we know that for any quantities, how many types are there? How many? So there is one type of quantity. One way to express the quantity is that what exactly do we need in order to express the quantity? So that is what we call. On the basis of that, we have got two categories of quantities: scalar and vector. If I want to see whether the quantity it can be broken down into further constituent components or not, on that basis I have got two categories of quantities. What are those? Excellent. So the next thing is base and derived quantities. So whether it is fundamental or not, okay, or it can be broken down or not. So I've got base quantities and I have got derived quantities. So for this I say can not be further simplified, and for this one I say can be broken down to, to constituent quantities. Constituent quantities. Okay. Then, sir, for base quantities, I say how many base quantities are there? There are seven fundamental or base quantities, and each of them they have got their standard unit. What's the So, for what are the seven quantities to begin with? So the first is length. Then you have mass. Weight is not fundamental. Weight is a force, so that's a derived quantity. Length, mass, time. What else? Temperature. That is quantity of substance. Quantity of substance. Um, Current, how many? One, two, three, four, five, six. One is still missing. That is length is same as distance. This is luminous intensity. So now, sir, the units for these quantities, the length, it would be measured in meters. That's the standard unit. Mass, it would be measured in kgs. time, SI unit is seconds, temperature, kelvins, quantity of substance, moles, current, amperes, luminous intensity, candela, CD as you say. Okay. All right. Amperes, usually the symbol I use is simply capital A, and for candela I use CD. Now for derived quantities, I can further say derived quantities, they can be a number of ways. A derived quantity which is combination of two base quantities. There could be a derived quantity which is a combination of a base and a derived quantity, and there could be a derived quantity which is itself combination of two derived quantities. Achha, I'm writing two for the sake of simplicity. Obviously there could be more. uh, Two as in combination of two quantities. It could be combination of three or more quantities as well. All right. So for example, we have got power. So the unit, the calculation for power is energy by time, and energy itself or work done itself, it is calculated force, distance, time. So force is a derived quantity, distance is a derived quantity. Sorry, distance is a fundamental quantity, time is a fundamental quantity. So it's combination of three, and you could have various such combinations. So if you could give me an example, please, for a quantity which is combination of two base quantities. Excellent. So we have got velocity, which is distance over time. Then, sir, for a quantity which is a combination of a base quantity and derived quantity, let's say acceleration. How? Because acceleration is delta v by delta t. So v is derived quantity, and uh, t is fundamental quantity, and as you mentioned, momentum. So momentum is mass times velocity. Mass is fundamental quantity, velocity is derived quantity. Excellent. Any quantity which is combination of two or more derived quantities. So you could say impulse. So impulse, no, impulse is force into time. Mm, let me think. Two derived quantities. What con? You didn't write for derived plus derived? I said that time also we couldn't remember. I couldn't remember. Chale, let me think. Maybe I'll be able to think one of now. Just a second. Let's do this time. Derived plus derived velocity. Force into velocity. So power can also be calculated as force times velocity. Why? Because power is force into distance by time. So distance by time is velocity. So power can also be calculated as force times velocity. Yes? Hmm, this is suddenly stuck. Why? Too much load on the system. Just a second. Working now. Okay. So, sir, we say power is equal to force into velocity. Why is it suddenly different? I don't know. Okay. This, sir, then we move on to the first thing that we have to do for I mean the first quantity that we have to study, which is motion. Okay, so regarding motion, what do we have? So I write over here Motion. Just a minute, please. I'm getting a phone call. All right, sir. We were discussing motion. Okay, so this is basically motion and related quantities. Motion and related quantities. So, first of all, sir, if I begin by the first concept, the definition of motion itself, how would I define motion? Distance is being traveled, and how would I know distance is being traveled? Work is being done? No, sir, that's not always the case. If something's moving with constant velocity, would some work be done? No. Motion, displacement. How would I know if there is displacement or not? Sir, the criteria is if position of object changes with respect to surroundings. With respect to its surroundings. Okay, so if I'm sitting in the car, the example that we used often in our class, and the car is moving, and the person who is sitting next to me, and I'm sitting idle, that person is sitting idle, that person suddenly looks at me, what would he say? Am I in motion or not? Okay, so if my surroundings are interior of the car, I'm not in motion. But if my surrounding is the external environment, if we look outside and then we look at each other, or I look at him with the outside in the background through his window, I'd say that we are both in fact in motion because we are changing our position with respect to these outside surroundings. So it all comes down to how do we define surroundings. Okay. uh hmm, 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 hmm. uh you I'll tell you something. Back in the day, I used to watch documentaries on Discovery and Nat Geo. So I remember one day they were showing this documentary. I don't even remember what documentary it was, but the scene that I remember, they had a big ring, and within that ring, they had a seat. Okay, so a circular round ring, and within that ring, they had placed a seat with a table in front of it. Okay, and they had people sit on this seat one by one. So the first person they had sit on this seat was a fighter jet pilot. Okay, and what they would do is they would set the ring in motion, so it would turn upside down, right, left, forward, backward. I mean, the ring would just move about, spin. Okay, different directions, and they would give some instructions to this person to type as his ring was spinning. So the pilot, he was easily able to write down all these things, whatever he was instructed to. In fact, he turned to and wave at camera or make gestures at the camera. Then they had an army person sit in the seat, and we could clearly see that the army person, he had this dizziness and he felt motion sickness. Yet he wrote what he was told to do, even though with difficulty. Then they had an average person who was not in military sit down in the seat, and within seconds, 5 to 15 seconds, he tapped out. He started vomiting and he couldn't do. So the idea that they mentioned at the end of our backbone, I think in I mean, I don't exactly remember the spot. There is this just single hair-like thing at the top of the backbone or somewhere in the brain at the backside. And that thing, it gives us orientation. I don't even remember, maybe you study biology, you'd know, but there is just this small component, a hair-like structure, and I remember it had to do with the backbone. It's at the top tip of the backbone, or it's somewhere at the back of the brain. Somewhere there's just a single hair-like thing. So that gives us orientation. If that thing is tilted right, left, so their theory was that since pilots, they are used to flying and they're used to maneuvering the aircraft, they feel they are used to getting this much disoriented. They don't even feel this much as disorientation. Okay. So they were able to type easily. As for the army personnel, their training is that they have to carry out whatever command is given to them. So even if the person he felt dizziness, he still was able to, yeah, he tried to carry out the command that he was given. As for the average person, he doesn't have the training where we compel him to carry out the commands that he is given, nor he is trained to be in that motion. So he couldn't survive that. I mean, he 5 seconds, 15 seconds into the test, he tapped out. So just remembered from your motion sickness point. Okay, so sir, we have definition of motion. Now, with regards to motion, the quantities that we have. What are the quantities that we use to calculate motion? There are two quantities. Uh, First is to calculate motion. The first one is distance, and the second one is displacement. And unit for both these quantities is meters, both for distance as well as displacement, right? Okay. Distance displacement unit is meters. Then the difference between distance and displacement, distance is scalar, and it is therefore in any direction. Okay, regardless of direction. Displacement, however, is vector, which means it has to be in a particular direction. Particular direction. Just a second. Hmm. Acha ji. So this is something that directly calculates motion. As for the related quantities to motion, the first one that we have got is so now these are quantities which are derived using motion. Okay, so the first derived quantity that we study is velocity. Hmm, velocity. Okay, sir. So, sir, if I have, and again, derived quantities, there is velocity and there is speed. How do I define speed? So, speed is distance per unit time, whereas velocity is displacement over time. So, sir, for these quantities, the things that we need to know are definition, we need to know formula, and we need to know graph. Okay, for each of them. Acha ji, so formula we have written, and definition we can do a number of ways. So for example, for speed I define as a rate of distance covered by an object. Okay, whereas for velocity I would say it is a rate of displacement again covered by an object here, displacement of an object. Acha, along with that, along with the formula, we need to know unit as well. So unit is meters per second since it's displacement by time, and the unit for distance by time is also meter per second, right? For velocity, there is another way we can define it as well, and that is since when we say displacement, it automatically we know displacement is in a particular direction, so we need not say it in a particular direction again. But if we say, we can equally define it as speed in a particular direction. Yes. So speed in a particular direction, that would also be velocity. ठीक है, rate of distance covered in a particular direction, that is also velocity. Let me write this as well. Rate of distance covered in a particular direction is also velocity. Understood, sir? Sir, then we move on to, so for distance. Achha, if we were to define distance, can I define distance in some way? Excellent. So for displacement, let me write shortest distance between 2 points. Oh, is the police outside or is it ambulance? Mhm. The shortest distance between 2 points, or I can say distance covered in a particular direction. But sir, both these definitions they make use of the word distance. How would I define distance itself? it is measure again space. Excellent. Measure of change of position of an object. Okay, so if an object is changing position, the way by which I measure how much has it changed its position, that would be measure of the distance covered by the object. Okay, and if the object is changing position, so for displacement I can also say measure of change of position of an object in a particular direction. Okay, wherever we write distance, instead I can say shortest change of position between 2 points, or change of position of an object in a particular direction. That would be displacement. Understood, sir? Now, sir, moving on to graphs. Okay, sir, first of all, we have got graph for let's say displacement with respect to time. Hmm, hmm, hmm. Let me draw it a bit neat. Just a second. Okay. Let me bring it over here. Excellent. Now, sir, I will have, I shall have displacement on y-axis and time on x-axis. So give me a second. Let me make a few copies of this one, because instead of drawing it over and over, I'll just try to use the same one. Just a minute, please. Come on. Time over here. And then I select Control C. Then I select over here Control V. Chalo. We'll fetch from there. Okay, so sir, now for displacement time graph, the first one would be just a horizontal line. So what can you tell about the motion of this object? Let's call it object A. Yes, sir. Any comments? This is a displacement time graph. So let me write. What's the difference between displacement time graph and speed time graph? In displacement time graph, we measure displacement against time. In speed time graph, we measure speed against time. So for this one, what's your comment about the motion of this object A? Okay, so object A is stationary. Good, sir. Sir, then what would be your comment about this one? B. Wrong. This would be constant velocity. Constant velocity. How do I know? So first of all, sir, uh, gradient. Gradient, which is m, is equal to delta y by delta x, right? So that would mean we are calculating change in displacement, which is on y-axis, over change in time, which is what? Which is velocity. Therefore, sir, I can say gradient of displacement time graph gives velocity, Mayer's velocity. Okay, and over here, since line is straight, therefore gradient is constant for a straight line. For A also gradient was constant. For A I could say m is equal to 0, and since m over here is velocity, I can say velocity is 0. Over here, since straight line, therefore m is equal to constant, which means velocity is constant. Agreed, sir? All right. Uh, then, sir, just a minute, sir. The That's it. Okay. All right, sir. So we have got constant velocity. We have got like this. Okay. Sir, if I were to draw a line like this, what can you tell me about motion of this object, sir? Hmm. 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 So, sir, how can I say that? So I'll say that along with my proof. My proof is that upward sloping curve. See, just a second, sir. I have put too much load on my system, so it is currently lagging. Okay, sir. So we say this is um, just a second. Should allow me. Acha, I changed it. Okay. Acha, ji. So I have got upward sloping curve. Upward sloping curve, uh, which then tells me that m is gradient is, where did it go? Astaghfirullah. Why is it like this? Okay, so every time it refreshes, it is bound to hang. Sure. Hmm. Upward sloping curve, so m is increasing. Since m is velocity, this would mean that velocity is increasing, and we have a name for this phenomena, that the object is accelerating. Okay, so sir, that tells me if the graph were something like this, then okay, so we can make the opposite comment about it. For example, sir, we would say uh, curve with decreasing gradient, right sir? Which means velocity is decreasing, and we have a name for this phenomena, which is deceleration. Make sense, sir? Hmm. Are you noting these things down, or are they already there in your notes? All right, sir. So this was for the uh, displacement time graph. Acha, if I were to draw one more over here, and this time I say it looks like this. Okay, make it this the same. What can you tell me about motion of this one? Yes, sir. For this object E. Hmm. How would you describe motion of object E? E, object E. So we would say, first of all, it is moving with constant velocity. Why? Because the value of gradient is constant, and it's a straight line, so gradient is constant. So the velocity is constant. But then what is the difference between B and E? What would be the difference between B and E then? So said the difference is difference of direction. Okay. No. Velocity is constant, so it can't have acceleration or deceleration. For there to be acceleration or deceleration, velocity is changing. Since velocity is constant because it's a straight line, it's not that velocity, it's moving in opposite direction with same velocity. Okay. So moving in opposite, or we can't say opposite direction. Opposite direction would be when we had gradient of same value but in negative. For example, if I extend this down and now I have an object. Hmm, just a second. Hmm, hmm. If I had this object, okay, let me give it a name. What name shall I give it? Let's call it E, yeah, F. Okay, so F would have, but for F, displacement is decreasing over time. Hmm. So F would have over there also. I think for E and F, both we can say they are moving in opposite direction. For E also we can say that they're moving in opposite direction, and I'll tell you why. Okay, sir, for B, gradient is positive, right? And for E, gradient is negative. Do you agree? So for both E and F, even though the displacement right now is positive, gradient is negative, and gradient is velocity. So velocity is negative, which means its velocity in opposite direction. Okay, so even for E, we can say that it has velocity in opposite direction to the object B. Okay, and all these other objects C and D, because their gradients at the end of the day, whether they are increasing or they are decreasing, they are still positive. Yes. For E and F, the gradients are negative. So that means velocity is negative, and negative velocity means velocity in opposite direction. Understood? But it's constant, it's in opposite direction, but constant velocity. Therefore, it's neither accelerating nor decelerating. Is that also understood? Okay, sir. Now we move to velocity time graph. Hmm, where did it go? Here it is. Hmm. Here we have the speed time or velocity time graph. So let me write over here. I have got velocity. Just then I use this shapes straight line. Sir, what can you tell me about motion of this object A? Constant velocity. So before moving further, let's also see the gradient. So again, m is delta y over delta x, which in this case is change in velocity over change in time, which is acceleration. Therefore, gradient of velocity time graph gives acceleration. Do we agree? And over here, constant velocity y, because m is 0. If I had to show an object with 0 velocity, how would I show that? Hmm. Sir, I would show this something along the x-axis. So it would have its value on x-axis. Anything over here, I would know it has got zero velocity. Okay. All right, sir. Then the next thing is if I have a straight line like this, what can you tell me about motion of this one? What about B? No velocity? Accelerating. So this one has constant acceleration. Why? Because it's a straight line, which means m gradient is constant, which therefore tells me acceleration is constant because m is acceleration, gradient is acceleration over here. Right, sir? Okay. So if I were to draw a curve like this, object C, what would you tell me about this object C? Hmm. Hmm. Object B is also accelerating. Constant acceleration means it's accelerating. So object C would have increasing acceleration. Okay. And we would say since it's an upward sloping curve, that tells me m is increasing, and since m is acceleration, therefore acceleration is increasing. Okay. All right, and then sir, you have uh, this one. Let's call it D. What would D be? Excellent. So it is decreasing acceleration, which you remember is different from uh, different from deceleration. So we would say since this mm, curve with decreasing gradient, therefore m is decreasing, which means a is decreasing. Okay, sir. All right. So, sir, we have studied the concept of displacement, we have studied the concept of velocity and we have seen their graphs. Okay, just a second. All right, all right, all right. Okay, then, sir, if the velocity, so far we have seen that there is constant speed or constant velocity, except for over here we came across certain instances where we saw that velocity or speed it is changing. Okay, sir. So if we have, just a second, varying velocity, okay, varying velocity, so that is what we call acceleration. Okay, and how do we calculate acceleration? Acceleration is equal to delta v by delta t, which is equal to v minus u by t. Yes, sir. All right. So this is acceleration. All right. All right. Acha, I think this pretty much sums up what we have for basic velocity and stuff. Tomorrow we shall start a class early. We shall do a bit extended class, and first we will study forces, or we'll see tomorrow that what we can do tomorrow. But what we have to do now onwards is that to build on top of this that we know about motion and velocity, what is the next quantity that we can see, and how does that fit into the picture? So we'll see that tomorrow. All right, sir. All right. See you tomorrow then, sir. Assalamu alaikum.